Translating human language into a rigid mathematical space requires a model to process billions of unstructured words. By 2014, two distinct methodologies had emerged to tackle this problem, but they operated on entirely different assumptions. The count-based camp relied on global matrix factorization, such as LSA. This method builds a massive grid tracking co-occurrence counts across the entire corpus. Because it looks at the whole dataset at once, it captures the global statistical structure of the language. However, these models struggled with word analogies. If you tried to calculate king minus man plus woman, the resulting vector rarely landed on queen. The global statistics were present, but the fine-grained relational geometry was missing. The rival camp used predict-based models like skipgram and word2vec. Instead of a global grid, they scanned the text through narrow moving windows, using a neural network to predict words based on their immediate neighbors. These models were highly effective at capturing linear analogies. The limitation here was the field of view. By training only on local context windows, predict-based models ignore the macro-level co-occurrence statistics that count-based models prioritize. This created a trade-off. Researchers could either utilize the global statistics of a dataset or capture precise micro-relational structures, but no single model did both. Jeffrey Pennington, Richard Socher, and Christopher Manning developed GloVe to bridge this gap. Their model, Global Vectors, was designed to incorporate the strengths of both global factorization and local window methods. Unlike word2vec, which relies on a tuned predictive architecture, GloVe is built from first principles. It is derived through a series of algebraic constraints. Structurally, the model is founded on a global word-word co-occurrence matrix, grounding it in the count-based tradition. But the derivation leads to a specific conclusion. GloVe provides a mathematical proof that count-based and predict-based models can be viewed as optimizing the same underlying objective. This theorem linked global statistics and local analogies into a single framework, providing a shared mathematical language for the two competing methodologies. Traditionally, models attempted to extract meaning from raw co-occurrence probabilities, the likelihood of word K appearing given word I. But raw probabilities are sensitive to the frequency of baseline words, making them a noisy signal. The GloVe paper demonstrates that meaning is isolated more effectively by looking at the ratio of two probabilities. By dividing one conditional probability by another, we can filter out baseline noise. When we test a probe word like solid, which is related to ice but not steam, the resulting ratio is 8.9. Conversely, when the probe word is gas, which correlates with steam and not ice, the ratio drops to 0.085. Noise cancellation occurs when the probe word is irrelevant to both, like fashion, or relevant to both, like water. In these cases, the baseline frequencies cancel out, and the ratio hovers near 1. To isolate distinguishing semantic features, the model's objective function must be structured to reproduce these ratios rather than raw counts. This leads to the derivation's starting point, equation 1. We define an unknown function f and set it equal to the probability ratio of our word vectors. We then apply 3 desiderata to determine the form of f. First is linearity. Because the ratio is a relative comparison, the function should only depend on the difference between the word vectors I and j. Next, we require a dot product. The left side of the equation contains vectors, while the right side is a scalar. The dot product allows us to map the vector space to a scalar output without mixing dimensions. The final requirement is symmetry. The model must treat center words and context words as interchangeable, as the co-occurrence matrix itself is nearly symmetric. Enforcing this symmetry requires f to be a homomorphism from addition to multiplication. The only continuous mathematical solution for such a function is the exponential. By making f exponential and introducing bias parameters to account for baseline word frequencies, the equation collapses into a log bilinear form. This derivation shows that GloVe's architecture follows directly from the decision to map vector differences to probability ratios. Equation 7 faces a practical problem. If a word pair never appears in the corpus, the log of 0 diverges toward negative infinity. Furthermore, very rare co-occurrences contain statistical noise that would degrade the quality of the vectors. GloVe frames this as a weighted least squares regression, minimizing the error between dot products and log counts using a specific weighting function. Crucially, this function ensures f of 0 equals 0. If a word pair never co-occurs, its loss contribution is 0. Because language co-occurrence follows a power law distribution, most cells in a word-word matrix are empty. By ignoring these 0 entries, the model avoids calculating most of the matrix. Training only touches the non-zero entries, resulting in a complexity of O of C to the 0.8. This allowed GloVe to incorporate global corpus statistics while avoiding the scaling limits associated with traditional matrix factorization. In Section 3.1, the paper provides a formal bridge between count-based and predict-based models. When skipgram is aggregated over an entire corpus, its objective is a weighted cross-entropy loss. If we replace that metric with least squares on unnormalized logs and replace its contact weighting with a generalized function, the skipgram objective becomes identical to GloVe's equation 8. This implies that the neural window approach of word2vec is implicitly approximating the same matrix factorization that GloVe performs explicitly through regression. The count-based and predict-based methodologies were simply applying different distance metrics and normalizations to the same global data. Empirically, GloVe achieved 75% accuracy on the linear analogy benchmark using a 42 billion token corpus, proving the derived model was competitive with tuned neural architectures. This result showed that the underlying training mechanics, whether count-based or predict-based, produced equivalent semantic maps when optimized over the same corpus. However, both GloVe and word2vec rely on a static one-word, one-point assumption. Every single instance of a word receives the exact same vector, regardless of its context in a specific sentence. GloVe represented the mathematical culmination of this static vector era. To advance further, researchers had to look beyond fixed mappings. This led to the development of models like Elmo and BERT, which use dense vectors but calculate them dynamically based on the surrounding text. GloVe remains the rigorous endpoint of the static embedding era, proving that semantic relationships are fundamentally encoded in the global co-occurrence statistics of the data.